One of the things that we can use Bohr diagrams for is to help us figure out number of valence electrons, and that's why I prefer that way of doing Bohr diagrams. So if you look at the periodic puzzles that we did the other day, you'll notice like everything in this first group has one valence electron in its Bohr diagram. Everything in group 2 has 2. When we get to the transition metals, they're a little bit hard to predict, so we don't use them. Everything in group 13 will have 3 valence electrons. So you just drop the 1 in front. 14 has 4. 15 has 5. 16 has 6. 17 has 7. And group 18 has 8, with the exception of our little friend over here, helium. So we can use the periodic table to help us predict valence electrons. It gets a little bit more complicated once you get past this third period. Basically, if there are more than 8 electrons in that circle, only the ones that are more than 8 are going to be part of that valence electron. So if we had 10 valence electrons or 10 electrons in that outside shell, only 2 of them would be involved in bonding because the other 8 are already happy and satisfied and aren't going to be part of that bond. So this is just a picture of the entire periodic table, and it's kind of hard to see. I don't really have a way to zoom in here, but it shows you as you get higher and higher how those valence electrons are going to react. But ultimately, we know that Bohr was wrong. We don't use the Bohr model of the atom anymore because it's not the best way to represent our electrons. And that's due to the Heisenburg uncertainty principle. So the Heisenburg uncertainty principle basically says that we can't know how fast an electron is traveling and where it's at the exact same time. We can only know one or the other. So for the purposes of these diagrams that we're about to look at, we're going to be looking at where our electrons are at, not how fast they're moving. As we go through these notes, you'll hear me talk about energy levels. And basically that refers to how far out from the nucleus our electron is. So first energy level, second energy level, third energy level. As we use those words, that just means we're getting further and further away from that nucleus. And those are going to match up to the periods on our periodic table. So first energy level would be the first period, second energy level would be the second, etc., etc. There are 4 different orbital shapes. The first orbital shape is the S shape. It basically looks like a sphere. So if you imagine like a beach ball, anywhere inside that beach ball, our electrons could travel. So Bohr thought that it was an orbit around that beach ball, but now we know that really anywhere inside that beach ball, our electrons could be traveling. So it's the S shape. Then we have the P orbital. The P orbital is basically a figure 8 pattern. And that figure 8 can exist in 3 planes. So that means it can go up and down, or side to side, or front to back. So those are the 3 planes it can exist in down here. So those electrons in a p orbital could be traveling in any of those directions. And then we have a d orbital, which is 2 figure 8 shapes, again existing in 3 planes, which means that there's a lot more possibilities about the way the electrons could travel. And then finally, the f orbital. The f orbital has electrons, 3 figure 8 shapes, and again existing in 3 planes. So lots and lots of opportunities for your electrons to go in different directions. Now, as we talk about those orbital shapes, we can have different sizes. So we might say it's the 1s, so 1 sphere, or the 2s, which is slightly larger. So in this picture, you'll notice right here there's this inner little circle guy, that's the 1s, and then this is showing you the 2s on the outside. So they can get more and more complex as we go. This picture is right here, you see the circle in the middle, that's a 1s orbital. And then this is a 2s orbital, so it's even larger than the 1s. And then we have a p orbital overlapping. So the p orbital is the figure 8 shape right here. And remember, it goes in 3 planes. So that's why you have it going this direction and that direction. So these diagrams will get more and more complex, and it's just showing us the way that the electrons are traveling. Now the good news is I'm not going to ask you the shapes. I'm not going to ask you to draw the shapes. I'm not going to ask you to identify the shapes. I'm just explaining the shapes so that you know why I'm asking you about all these letters. What I will ask you to do is know how many electrons fit in each shape. And we can use the periodic table actually to help us figure this out. So elements on the periodic table are assigned to different blocks based on the shape that their electrons would be in. And so we have the S block, the P block, the D block, and the F block. If you notice, the S block is 2 elements wide. Over here, the P block is 6 elements wide. The D block is 10 elements wide. And the F block is 14 elements wide, which is exactly how many electrons will fit in each of those orbitals. So by knowing which part of the periodic table is which, you already know which or how many electrons it'll fit. So if on your periodic table, if you will label the S, P, D, and F blocks, that will help you a lot later on. You'll notice helium, once again, being weird over here, not fitting in where it's supposed to. It's actually part of the S block. It just appears on this side. But if you'll label S, P, D, and F somewhere off to the side of your periodic table, we're going to be using that a little bit later on. So there's 3 principles that go into play when we are going to do these orbital diagrams. And an orbital diagram is basically something that looks similar to this. It is going to tell us how many electrons will fit in each section. And the Aufbau Principle is the first rule that we're going to apply. And it says that electrons will occupy the lowest energy level available first. So I gave you a picture on your notes of the different orbitals. Basically, as close as we can get to the nucleus, we're going to be following the Aufbau Principle. So think of going to a concert for your favorite band or something like that. You're going to want to sit as close to the stage as possible. And the stage in this case is just the nucleus. So we're going to sit as close to this 1s orbital as possible. That's where we'll go first before we work our way up. Now, some of the orbitals actually overlap, and that's what this shows us. So you'll notice as we go down, if we were to follow these arrows, it goes from 3p to 4s to 3d to 4p, and they don't actually go in order. And that's the same thing that we see right here. So sometimes they're not going to go in order of the number. They're going to go in order of the height that we see on this orbital diagram. So you just want to fill it in bottom to top. Don't go side to side. Second rule we're going to apply is called the Pauli exclusion principle. And it says that if 2 electrons have to occupy the same orbital, that they're going to go in opposite directions. So imagine putting a pair of shoes in a box, a pair of heels or boots or whatever. You're not going to be able to make the heels face the same direction. They're going to have to go opposite directions in order to fit in the box. And that's essentially what this rule says. And then the third rule is Hund's rule. And it says that electrons are going to spread out before they share a space. So think about going on a road trip, and you're on that road trip with your friends, and there's 3 of your friends, and you're the driver. Nobody's going to sit and cram themselves in the back seat when shotgun is available. And that's basically what Hund's rule says, is they want to spread out before they share a space. So if we were filling in these 3 orbital diagrams, basically what this is saying is that my arrows are going to spread out before they go back and share in the same box. So this would be my first arrow, second, third, and then my 4th arrow, if it had to, would go back and share that box. But they spread out before they share. So we're going to fill in the orbital diagram for sulfur. Orbital diagrams are going to represent electrons, so we need to know how many electrons there are for the element sulfur. Sulfur is number 16 on the periodic table, and so that means it has 16 protons, and if it's neutral, it's also going to have 16 electrons. So I'm going to fill in this orbital diagram. So there are 16 arrows. I'm always going to start at the bottom. I'm going to spread out when I can. And I'm going to go an opposite spin if I cannot spread out. My first arrow is always going to be an up arrow. So 1. There's no more space in the 1s for me to spread out. So that means I will share a box. So that's my second arrow. Now that this orbital is full, I'll have to move up to the next one. So 3 and 4. Now I move up again. 5. Element number 6, or electron, sorry. Electron number 6 is going to spread out because there's space for it to do so. So 6, 7. Once you can't spread out anymore, then you'll share the same box. So that was 7, 8, 9, and 10. Now I'll move up. 11, 12, 13, 14, 15, and 16 would go the opposite direction. So that is the orbital diagram for the element sulfur. If you will give the element selenium a try, go ahead and pause the video right here. Give it a shot, and then as soon as you're ready, if you'll push play, I'll go over the answers. So for selenium, selenium is number 34 on the periodic table. You should start at the bottom, work your way up. But right here, make sure that you've spread out your electrons at the end. Remember that last one will share a box because it can't spread out anymore. So that was an orbital diagram. Now we're going to talk a little bit about electron configuration. So electron configuration is basically a shorthand version of an orbital diagram. So essentially this is the map, and now this is just going to be the written directions. It says that you need to know this long, crazy list for your test. That is true, but the good news is you don't need to memorize it. I'm going to show you over the next couple of videos and days how to figure this out using the periodic table. So we're going back to our element sulfur. So I said this is the map, and now we're going to write the instructions. So basically what we're going to do is we're going to list the number, the letter, and then how many arrows or electrons there are in that box. So this is the first period, the s orbital, and there are 2 electrons represented there. Then if I look right here, I have the second period s orbital, again with 2 electrons. I get up here to the 2p, so 2p, and then there are 6 arrows, so 2p6. Next up is 3s2, and then in the third period, there are 4 arrows, so 3p4. So that's the electron configuration for the element sulfur. You will give selenium a try, and then as soon as you're finished, go ahead and click play, and we'll go over it. So for selenium, you have a much longer list to do, but you should have ended up with 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, and 4p4. The homework for tonight is to create an orbital diagram and an electron configuration for each of the elements that is up there on the screen. So neon, sodium, chlorine, and then your element that you have for your element project. Assuming your element is not larger than 55. If it is larger than 55, you can choose any other element that you want to do. Or if your element is already up there on the screen, you can also choose any other element. And then you're going to do the board diagrams that are on page 89 and 90.